Welcome back to our discussion of synchrotron radiation. So we've just looked at the dynamics of a single charge particle in a magnetic field, and we talked about how it makes spirals in the magnetic field because the Lorentz force does no work, and so the magnitude of the velocity doesn't change, and therefore the Lorentz factor, the gamma, doesn't change. And when we get to radiation, we'll see that actually the Lorentz factor will change, but that's a separate effect that's not to do with the dynamics. So we derived in this particular case the fact that it makes these circles or these spirals around the magnetic field. We derived the radius of the circular motion. That radius is called the Larmor radius, and we derived an expression for that Larmor radius in terms of the Lorentz factor of the particle, the mass of the particle, the perpendicular speed, which is just the component of the velocity vector that is perpendicular to the magnetic field in terms of the charge on the particle and the magnetic field itself. And then we also derived the angular gyro frequency, which is the frequency of this, the angular frequency of this orbital motion of this charged particle as v over r, and that's qb over gamma m. I'm just going to define this angle alpha as the angle between the velocity vector and the magnetic field vector, and we'll use this in a couple of other cases. So this Larmor radius, let's just talk about an example of where this might be relevant. In astrophysical plasmas, this Larmor radius is important, for instance, in high-energy astrophysical situations where you're producing charged particles. They are in regions of magnetic field, and they're trying to escape these regions of magnetic field. And so if of course, as they are trying to escape, the magnetic field curves their paths and kind of traps them into a region of size r. So this radius r is actually an important concept for people who study cosmic ray astrophysics. And so let's just briefly discuss that. So that is this trapping radius for cosmic rays. So cosmic rays being high energy charged particles that are being produced in some energetic volume of space. And so this trapping radius r for a given region of space with some magnetic field b is given by this Larmor formula, gamma m, and instead of v perpendicular, I'm going to write v sine alpha, where alpha is this angle between v and b divided by q times b. And so you will remember gamma mv, of course, is just the magnitude of the 3 momentum. So we can write this as the magnitude of p times sine alpha divided by qb. And the reason I'm writing that in that form is going to be obvious in just a second. And that's because I'm going to multiply and divide by c, the speed of light. And then this quantity, r, this trapping radius, can be written as p times c, the magnitude of pc over q, times sine alpha over b times c. This one is equation 7.6 of high-energy astrophysics, and it's a named or numbered equation because it's relevant to keep in mind these two different aspects, one of which depends on just the properties of the particle, and the other which depends on the magnetic field, of course, with this pitch angle alpha in between. So this quantity, Pc over Q, has a name. It has a terminology in high-energy astrophysics that I just wanted to introduce to you. This thing is called the rigidity. The rigidity of the particle, and you can see that it is a more rigid particle, has a higher momentum or a smaller charge, and it just means that it's deflected less by the magnetic field. So more rigidity means that it has a larger radius and is more likely to escape that volume without getting trapped. Of course, if this r is smaller than a given volume, then the particle's path gets curved enough so that it gets trapped within that region of space. So the larger the rigidity, the higher the more likely it is for the particle to escape. And you can see that more energetic particles are more likely to escape a region of magnetic field. And therefore, that's why this rigidity quantity is important. Another thing to keep in mind, just as a warning, is just keep in mind when we talk about these gyro frequencies, whether we're talking about the angular gyro frequency, which is qb over gamma m, or we are talking about the linear gyro frequency, which is qb over 2 pi gamma m. And finally, one more word of warning for if you're using these equations in your code and you're calculating these quantities from scratch, just keep in mind what unit system you're using, because these values depend upon whether you're using CGS units or Gaussian units, or whether you're using the SI system. So in the SI system, the formula that I'm deriving here will mostly be in the SI system. I'll let you know if it's in the CGS system. In the CGS system, there will be various factors of the speed of light running around. And in fact, the two different references that we are using for these videos, which is high-energy astrophysics and Rybicki and Lightman, use different unit systems. And so just as a reminder that the two different books will have slightly different equations. All right, so having discussed these dynamics in some level of detail, we are now going to move on to discussing the radiation from this particle. So let's talk about the radiation from a single particle in a magnetic field. So we're talking about what kind of radiation you might get out of this. And here, I'm going to simply write down the formula of the radiation power. And this formula is one that you've seen before if you're taking this as part of a course. And if you haven't seen this before, then I will point you to where you can see this later in the prerequisites discussion. So the radiation power depends upon the acceleration that the particle is experiencing. And so this E is the energy of the radiation, or energy of the particle as it is losing it as a function of time. So dE dt is given by this formula, which is called Lamar's formula, and is q squared mod a squared divided by 6 pi epsilon naught c cubed. So this is the rate, this is the power that's being produced, it's the rate at which the energy is being lost. Q is the charge of the particle, 6 pi epsilon naught, because of epsilon naught is the vacuum permittivity, c is the speed of light, and a is the acceleration of the particle. Now this has nothing specifically to do with synchrotron radiation. Just as a reminder, this is a general formula for the radiation that is produced by any charged particle, that's what the Q is, undergoing any acceleration. So any charged particle that accelerates radiates with that power. And in this particular case, we're going to apply this to synchrotron radiation using the acceleration that we derived from the dynamics discussion that we did last time. Okay, so this is all fine and good in the sense that the previous times you may have applied this formula is in non-relativistic situations. The one difference between the application in this case and other cases like in thermal Bremsstrahlung or elsewhere, is that this radiation power, or the energy lost, is in the rest frame of the particle. So properly, we should put primes on these quantities where this dE, dt, the energy, the time, and the acceleration are measured in the rest frame of the particle. Okay, so and you'll ask, what is the acceleration in the rest frame? It's the acceleration in the instantaneous rest frame of the particle. So you go into the instantaneous rest frame of the particle where it's given it's got a velocity at that time, and you figure out what the acceleration is. So in principle, we should have these primes. So this is in the rest frame. So that's what the primes mean. And so what do we do with this? Well, we need to do some Lorentz transformations. So the left-hand side is actually easy. It turns out that dE over dt is actually the same as dE over dE prime over dt prime. And that's because both energy and time transform the same way. And this is a discussion that is part of the relativistic astrophysics section of a course. If this is if you're taking this, watching this video as part of a course, or this is something that you can check. Both energy and time transform in the same way. Okay, so what do we do with acceleration? This one is harder. So the acceleration, it transforms in the following way. The transformation of the acceleration depends upon whether you're transforming the parallel or the perpendicular component with respect to the magnetic field. So with respect to a given direction. And so here's what the transformation looks like. So A prime squared, mod squared, is A, which is just A. You can decompose this into the parallel and perpendicular components. A perpendicular prime squared plus A parallel prime squared. So I'm just decomposing the acceleration into parallel perpendicular components. And then each of these transform in different ways. So this looks like gamma to the fourth A perpendicular squared plus gamma to the sixth A parallel squared. So here I've dropped the primes and I've transformed the parallel and perpendicular components from the prime frame to the lab frame, the unprimed frame. Okay, so let's put this into let's use this in our particular case of a charged particle that is moving with some speed gamma v along some direction at angle alpha with respect to the magnetic field. And so what does that look like? So our dE dt in this particular case, dE dt will be q squared and then the acceleration squared. So we have to take this thing and we have to substitute this in because this is acceleration squared already. So that gives us a gamma to the fourth, which I'm just going to pull out, over 6 pi epsilon naught c cubed from Lamar's formula, times a perpendicular squared plus gamma squared a parallel squared. And this is equation 6.25 of high energy astrophysics. Okay, so this is the general formula for a charged particle with some acceleration. We still haven't applied the specific case of a synchrotron radiation. So all we need to do that is to put in the corresponding values of acceleration, or corresponding expressions for acceleration. So what does the acceleration look like? Remember that the acceleration now, the parallel and perpendicular components are with respect to this magnetic field here. So the perpendicular component of the acceleration is the component that we used to derive Lamar's formula, and that's the component that's into the plane of the board. And there is no parallel acceleration. So A parallel is 0, and A perpendicular, as a reminder, A perpendicular for our case is QV perpendicular B over gamma M, and A parallel is 0. So in our case, dE dt, the power that we get is q squared gamma to the fourth over 6 pi epsilon naught c cubed times q squared v perpendicular squared b squared over gamma squared m squared, where I've just put in this acceleration squared. And this gamma, these powers of gamma come from this Lorentz transformation. So just collecting various powers, so that's q to the fourth over 6 pi epsilon naught m squared c cubed, this might start looking familiar, times gamma squared v perpendicular squared b squared. And just for fun, I'm going to multiply and divide by some factors. So this is q to the fourth over 6 pi epsilon naught squared m squared c to the fourth power, multiplied by c times epsilon naught, but I'm multiplying by dividing by a factor of c and by a factor of epsilon naught, times I'm going to multiply and divide by a factor of 2 mu naught, you'll see why in a second, and then we have this b squared, so that's b squared over 2 mu naught, times the remaining stuff here, which is gamma squared v squared over c squared, and then sine squared alpha. So the sine squared alpha comes from this v perpendicular squared, this gamma squared comes from here, and then I've just written additional factors of v squared over c squared, and I'm going to multiply this by c squared. So sorry, we're running into the edge here, but this epsilon naught c has been multiplied and divided here, 2 mu naught multiplied and divided here, v perpendicular has become v sine alpha, that's squared, then I multiply and divide by c squared, that's all I've done here. Okay, so why did I do all of this? Well, have a look at this and see if this makes sense to you. Do you notice any interesting terms in this product? So the first question I will ask, and take a moment to think about this, is that, what is that term? And you may recognize this. This term is nothing but, this is the Thomson cross-section, the Thomson cross-section for the electron. You may also be familiar with this. This term, b squared over 2 mu naught, is the energy density over the magnetic field. This term v squared over c squared, we're going to write as beta squared, where beta is v over c, is just the speed of the particle in units of the speed of light. Okay, and then this stuff, so epsilon naught and mu naught, so remember that epsilon naught times mu naught is 1 over c squared, so that cancels the c squared here. So you have 2c sigma t b squared over 2, and then of course these this 2 cancels, Oh, no, I should not cancel that 2 because that 2 is part of this 2 mu naught. So that's important too. We'll be stuck with that 2. Okay, let's put that 2 back where it belongs. Okay. Right. So at the end of this process, our dE dt is 2 sigma t c from this remaining c times beta squared gamma squared ub sine squared alpha. And this is p rad, the power that is radiated by this charged particle. Okay, so this is one of the key formulae that we've derived. This is equation 8.8 of high energy astrophysics. And it tells us the radiation power from a single charged particle in a magnetic field where the magnetic field has been subsumed into this quantity UB, which just is the magnetic energy density, moving at some pitch angle alpha with respect to the magnetic field direction. Now, there's another version of this formula, or another form of this formula, that is often used, perhaps more frequently than this formula. So I'm just going to describe that in a second. Let us take out this top bit. And so that is keeping in mind that in general, so there are two aspects in which this formula is modified to give you the same result. And those two aspects are the fact that in general, magnetic fields aren't like straight like that, right? They kind of are tangled around, or the particle that is moving through may scatter off of other particles or inhomogeneities or something like that. And so in other words, the pitch angle might actually change with time or with, from place to place as the particle radiates. That's one aspect. Or it's possible that the radiation that we are receiving is actually received from many different particles, all moving at different angles with respect to the magnetic field. So in both of those cases, this pitch angle alpha is something that we should average over. And so oftentimes, and really you should do this in the final spectrum, and actually we'll do that when we get to this final spectrum. But sometimes people do that just to this formula, and that also is meaningful for a single particle that's getting scattered. And to do that, what you need to do is you need to calculate the average of the sine squared alpha as this particle is getting scattered. And so all you need to do there is calculate the average of sine squared alpha over all solid angles, over all omega, over all possible angles that this could have. And I'll feel free to pause this video for a second and calculate what this might look like. I will write down the general expression of this for you. It's 1 over 4 pi integral of sine squared alpha d omega over all omega over all solid angles. So take a moment and see if you can calculate this, and then we'll proceed. So if you calculate this expression, this d omega you can just write as 2 pi sine alpha d alpha, and now our z-axis is oriented with respect to wherever we define alpha, and that's the same thing that we did here, right? So our z-axis is along the magnetic field. So this theta angle becomes this alpha angle, and this gives you a sine cubed alpha, which you can integrate. And so this is minus a half of the integral from 0 to pi of 1 minus cos squared alpha times d cos alpha, and then that is you can do this and you will get 2/3. So skipping a bunch of steps, this gives you 2/3. So you can put that in here, and you'll see that the average of p rad over all alpha, average over all these pitch angles, is equal to 4/3 sigma t c ub beta squared gamma squared. And now, of course, there's no sine squared alpha because we've just averaged over that. This is equation 8.9 of high energy astrophysics. And these two are quite very relevant equations that we want to keep in mind. Okay, so what have we done? We've just taken the actual acceleration of the particle, which we derived from the dynamics. We put that into Lamar's formula, and we use that to calculate the radiation power that you get out from a single charged particle in a magnetic field. And we see that it is proportional to the Thomson cross-section, which, remember, the Thomson cross-section depends upon the mass of the particle. So if you have a different particle that's doing the radiating. If you're talking about electrons versus protons, this cross-section will change. Times a bunch of, some fundamental physics, so the speed of light, stuff that depends on the speed of the particle, beta squared, gamma squared. In general, we'll be talking about ultra-relativistic particles, so beta will be of the order of 1, or gamma is going to be very high, so we might often drop this beta squared, but in general, you should have both beta squared, gamma squared, the product, and then UB, the magnetic field energy density, and sine squared alpha is the pitch angle. And then when you average over the pitch angles, you get this 4/3 sigma Tc UB. Keep this in mind when we talk about inverse Compton radiation, or if you look at inverse Compton radiation separately, you will notice something, the radiation power looks similar, and then it's interesting to see why you get something similar, but that's a story for another time. So the next thing we'll do is we'll discuss how this affects the radiation of, how this affects the cooling of a particle, because of course the particle is radiating, so it's losing energy, and then we'll talk about how what the spectrum of this radiation looks like from the single charge particle.